Calculus Unit 5, Day 43 Notes, Part 2. Before we proceed, the connection needs to be made, and I kind of made this connection already at the end of Part 1. But when given a function f of x, how do we find the slope of the secant line in the interval from x equals a to x equals b? In terms of position of a particle, to what does the slope of the secant line correspond? To what does the instantaneous velocity correspond? So we've already talked about this, and I'll talk about it in a second. If I have some function, it doesn't matter what that function is. If that's my function, the secant line is the slope of this line that connects the endpoints. And again, it's change in y over change in x, which if that was my position function, that's what it would look like. And that is considered the average velocity. Now, the slope of the tangent line at any point, doesn't matter where I am. So if I make my point up here, slope of the tangent line right there, that is the derivative of this function at point C. Okay, and that's known as the instantaneous velocity. So the derivative is the instantaneous velocity. Secant line, slope of the secant line is the average velocity. Okay, now let's get into average and instantaneous acceleration. Okay, well, hopefully we see a little connection here that the average acceleration on an interval, closed interval, from A to B is rise over run of the velocity function. So we have position, slope of the secant line leads to average velocity, and then the slope of the tangent line of the position function leads to instantaneous velocity. Now, average acceleration is the secant line of the endpoints of the velocity function. Again, v of t is the velocity function. V of t is also equal to the derivative of the position function. So average acceleration is the slope of the secant line, and now instantaneous acceleration is at some point when time equals c is the derivative of the velocity function, which is equivalent to the second derivative of the position function. Okay, so once again, this is, let's write this out, slope of the secant line, slope of secant line, and we'll be using these for a couple more unit lessons here, and this is the slope of the tangent line. Slope of tangent line and slope of the tangent line of the velocity function, which is the same as the second derivative of the position function. Well, this is the slope of the secant line over the interval a to b of the velocity function. Okay, and that's what this comes in right here. Okay? All right, so let's do this example, which is building off of the same position function that we did last one. P of t equals e to the t times sine of t. And again, P of t is measured in centimeters and t is measured in seconds. What is the average acceleration? Average acceleration is the slope of the secant line of the velocity function. This is the position function, so I have to use the derivative. So we found the derivative in the last time we did this to be e of t times sine t plus e of t times cosine t. And again, the velocity function equals the derivative of the position function. So now to find the average acceleration, we're going to just use the slope of the velocity, the secant line of the velocity function. v1 minus v3, that's change in y, over 1 minus 3, that's change in x. And we'll just put this in the calculator, 3.756 minus negative 17.050, and that's all over negative 2. And we're going to get something a little bit above 20 divided by negative 2 is going to be negative 10.403. Oh, I didn't need to underline that. And that is centimeters per second squared. Okay, because that is acceleration. All right. Now let's do the instantaneous acceleration. Again, what is instantaneous acceleration? That's the derivative of the velocity. We just said this is the velocity, so now I have to take the second derivative of that original function. And let's do that. So we just said the derivative of the position function is equal to the velocity function is equal to e of t sine t plus e of t cosine t. So now I got to take the derivative of this, which again I should have written it the other way, which is really the second derivative of the position function. And we're going to get e of t sine t plus e of t cosine t. And again, this is just the product rule of that. Plus, now I take the product rule of this one, e of t cosine t, and it's going to be plus e of t negative sine t, which I'm just going to write as negative e of t sine t. Now let's do some simplifying. So this positive e of t sine t cancels out with this negative e of t sine t. So what am I left with? I'm left with the derivative of the velocity function is equal to 2 e of t cosine t. Whew, I had to do all that. Now to get the instantaneous acceleration, I have to substitute in 1.5, which is equivalent to the acceleration at 1.5, which is going to give us, and we'll put that into the calculator, and we get 0.634, and we're talking acceleration, and that's going to be centimeters per second squared. Okay, so make sure you take a second to just verify that on the calculator.